Is this off? Yes, it's off.
To the first speaker this afternoon will be Antoine Choffrut, who will speak about weak solutions to the stationary incompressible relaxation.
So I'd like to thank the organizers for the opportunity to speak on some recent results on the method of convex integration as it applies to the stationary Euler equations. And this is going to be joint work with Laszlo Szekelyhidi. So this is a workshop, or actually a mini workshop, so I'm taking the excuse to make the presentation rather light, I hope. It will be mostly non-technical, only towards the end a little bit, and there will be lots of pictures to explain and convey the ideas. So to begin with, I'll start with some context and start with the time-dependent Euler equations for motivation purposes mostly. So we're considering the Euler equations which govern the evolution of the velocity vector field. So V here is the velocity vector field of an ideal fluid. That means it's incompressible and moves without friction. P in the equation represents the pressure enforcing the divergence-free condition. And so unlike the Navier-Stokes equation, there's no viscosity term. So a priori, there's no dissipation of the kinetic energy. So kinetic energy is the integral of the square magnitude of velocity field. And indeed, by routine calculations, you check easily that at least for sufficiently regular solutions, say classical solutions, the kinetic energy is conserved along the flow. That being said, Unzager proposed or postulated that there exists a mechanism for, he says, total dissipation of kinetic energy even in the absence of viscosity. And he proposes, or he postulates, a precise threshold between two regimes, one regime of rigidity, I will call it, where all solutions of class Hilda with an exponent bigger than 1/3 must conserve energy. And that was proved by Eink and Constantine TT in '94. And on the other hand, for if you look at among solutions of regularity less than 1/3, he says that there should be solutions which dissipates energy. So unlike the positive part of the conjecture, this is still incomplete, and there have been significant progress only in very recent years. I'm only making a very short list of contributions, and much of this owes to the work of Lellis and Szekelyhidi. Also, there have been some recent contributions of Philip Isett on the one hand, also Tristan Buckmaster, who will speak next, and also jointly with Lellis and Szekelyhidi. And as things are developing quite quickly, this diagram is incomplete, and they've had the bad idea of coming up with more results, and I didn't want to change my diagram, which took me quite a bit of work to do. So Tristan will certainly give more, clarify this situation. And this is not the purpose of my talk. It's mostly motivational, so he will tell you more on what's going on here. And in particular, there might be some more subtle issues as to exactly what the threshold should be. But again, this is not purpose of my talk. Let me list a few names of some of the people who since, well, in recent years have done some work in connection to these two convex integration in various forms. This is not exhaustive as it's getting more difficult to keep track of everything that's being done in the area. There's a growing interest in this area, so I'm just mentioning some of the names there. And for stationary Euler, just for presentation purposes, I've proved with Müller-Sverák a kind of analog of the rigidity part for stationary Euler to the effect that that smooth solutions are organized in a very precise way. And today what I want to talk about is an H principle for weak solutions and particular L infinity solutions. I will explain all these things, H principle and convex integration for a large portion of this talk. And of course, as I said, this is joint work with Laszlo Szekelyhidi. So let me state immediately the main result. So we're working on the torus for simplicity, but this is not a restriction at all. So you start with a smooth stationary flow. And by the way, I've rewritten the equation in this form. It's quite standard in the field. So just to be sure, so from v dot, so we drop the time derivative because we're in the stationary case. So the equations would be these, and using the divergence-free condition, we can rewrite this as equivalently as the divergence of v tensor v plus grad p equals 0, and divergence of v is 0. So you can see immediately that there is a meaningful weak formulation of the equation without requiring derivatives on v. And just for, again, to clarify notation, so v is a vector field. V tensor v is simply the matrix v, column matrix multiplied by the row, column vector multiplied by the row vector, and divergence is to be taken on each row. So we start with this reference smooth steady state with pressure P0. You fix what I call an energy profile E of x, so it's a function which is straightly greater than v naught of x squared, and you fix a parameter sigma which is as small as you wish. Then we construct infinitely many solutions of class L infinity, which satisfy, on the one hand, this energy profile almost everywhere. And secondly, those solutions are as close as you wish to the original steady state, but of course in some weak topology. So in what sense is this an H principle? So the H principle was developed by Gromov out of the work of Nash on the isometric embedding problem. And I'll describe with cartoon pictures what it is. The idea is the following. For certain types of problems, if you want to construct solutions, you start with something which is not a solution. It's called a subsolution with certain properties. And you deform it, or you bring it to a solution along a homotopy. So the H of homotopy gives the H of H principle. Now, typically, you get not just one solution, but in fact, infinitely many solutions, and furthermore, a dense set of solutions. And later on, I'll make a more precise statement to that effect. Now, what I mean by an H principle and the main result that of a previous slide is slightly different. First, we arrive at solutions not by a homotopy, but simply by an iteration. Okay, and what we are interested in is the abundance of solutions. The statement that there is a dense set of solutions. And for us, an H principle is a statement that there are many solutions. And we've abandoned the topological viewpoint, although you could easily reintroduce it. But this is not sort of the focus of this part of the community. Again, okay, as I said, there's infinitely many solutions. And also at the technical level, we use a different version of convex integration. So Gromov developed a convex integration scheme to prove H principles in the class of continuous functions. And what we are doing is an adaptation of those techniques due to Stefan Müller here in the room and Müller-Sverák. And yeah, so H principle for us is
actually an infinity case. Gromov has an exercise.
okay.
Or he says this can also be done in
So to summarize, these concepts is clarify the ideas, and H principle is a statement for us about the density of solutions, and convex integration is going to be a technique to construct those solutions. And in particular, we're going to establish an H principle using convex integration. This is just to clarify a little bit terminology. So just two examples to show that these things about H principles are perhaps not so unfamiliar. Is standard functional analysis that the unit sphere in, say, little L2 or more general Banach spaces is weakly dense in the unit ball. Okay, so you've probably all seen this. So it's actually close. I mean, the same cartoon picture as the H principle that I had earlier. And another example, which is more closely related to what I'm going to present today, is the example of Weierstrass of a function which is continuous but nowhere differentiable. So the reason I'm showing explicitly what it is that it shows the important features of this type of construction. It's you pile up faster and faster oscillations with suitable condition on the parameters. So Weierstrass published this one example, but of course there are infinitely many of those. And in fact, you can show that any continuous function can be uniformly approximated with functions which are continuous but nowhere differentiable. So you have already there your density statement. So it's something that actually, in some sense, was already there. Now you can do this, you can prove this kind of statement either by hand or using a Baire category argument. And for the result I'm presenting today, the form of the Baire category argument that I'm using, that we are using it due to Bernd Kirchheim, also drawing on some previous work, in particular due to Da Corogna and Marcellini. So that was for parallel analogies to show that these things are perhaps not so. You may have seen these things before, actually. So how do you put in place the convex integration scheme for the Euler equation, or the stationary Euler equation? We follow a very standard systematic operations. This is the framework, the so-called Tartar framework. So you start with your nonlinear problem, and you extract out of it a linear problem simply by substituting for the nonlinear thing a new unknown. So here B is a d-dimensional vector field. B tensor B, as I said, is a matrix. So that's your new unknown. And for technical convenience, we subtract the trace of this matrix and we transfer it to the gradient term. This is for technical convenience. One simplifying assumption, which is not essential, but it simplifies the presentation and it just induces more technical complications not to do so. We'll assume that the energy profile E of x is constant and equal to 1. And recall that we want, so this E of x, so E of x is straightly bigger than V naught of x squared, and we want to construct solutions with Vx squared precisely equal to E of x. This for a recollection. With these observations, let me introduce the constraint set K. So this is the set of V's and U's, which are related precisely according to this constitutive law. And also it incorporates the energy profile that I've entered here. So in summary, you have a solution to your nonlinear problem, and I didn't write subject to the energy profile, exactly when you have a solution to the linear problem, which furthermore satisfies this pointwise constraint almost everywhere. So I'll write it on the side because it'll be useful to have it for later reference. So VP solves, and I'll write this as nonlinear schematically if and only if something different but related to VP, so here it's V, U, Q solves the related linear equation plus satisfies the energy, the pointwise constraint. Okay, so we formalize things a little bit. What's next? Okay, so I'll give the first illustration of the convex integration scheme. This is not exactly the one that will be used, will actually be applied, but it's convenient to massage some ideas. So if we followed the scheme of Nash and Gromov, what would we want to do? So the convex integration scheme is an iterative method. Suppose that along your iteration you have at step n a solution or sub-solution, so something which solves this linear problem, and all of, the values are all inside this shaded region. And here, note that the set K is represented by the boundary of this set. And maybe I should clarify that this is space of the images. So there are two things. One is a physical space. So it'll be omega, which is the torus for us, and then x would be a point in physical space, and then v. So v u q or v u here takes values inside this other space. Okay, so here, let's say that at step n, all the values of the nth iterate are in this shaded region. The idea is that at step n plus 1, you want to bring those values closer to the set K. So from here, there, you want to push these values closer to the set K. And if things work well for you, and you can do this indefinitely, then you can imagine that in the limit, you have a solution to your problem because all the values are on the set K. And I'm using this characterization. Okay, so that's convex integration if you follow Nash and Gromov. And now the more precise illustration of the version that we are using. So similarly, you start with, say, a subsolution where the values are all in this moderately gray region. Know the difference that now K is the union of three disjoint components. And what I call U here is, for the moment, the convex hull of K. And again, what we want to do is, along the iteration, bring the values from this region to regions closer to the three components of K. And if you can do this, well, the scheme that is involved is able to do it in the sense that the darker regions get closer to the portions of the three components of the set K, and they get darker. But you also have some values in a bigger region, but which is lighter. So the color coding is as follows. When the region is darker, this means there's a larger portion in physical space where the image lies in here. And if the color is lighter, it means there's a smaller portion in physical space where the image lies in this bigger region. But in the limit, this is completely washed out, and you're left with just values in the three components of K. So this is just for a cartoon picture to explain the scheme. So how do you actually implement the scheme? Again, so what you do is you fix a point in physical space, a small box around it where the values are approximately constant, represented here, and you want to replace inside this box the values with values closer to the set K. So I'll again digress a little bit and show I think the simplest example showing the basic phenomenon exploited in the convex integration scheme. So you have here in the plane a straight line with constant speed represented by this green arrow. And what you want to do is to approximate this straight line with curves which take with velocities where the velocity has to be either a or b in this diagram. So it's easy. You go along a and then b. If you want to be closer to the original green curve, you alternate faster, and if you alternate sufficiently fast, you remain as close as you wish to the original curve. If this works, it's because phi prime of x, or the original velocity, is in the convex hull of A and B. And more generally, you can easily convince yourself that what matters is that you just need to alternate between A and B in a ratio which is dictated by the relative distances here and there. And in a sense, convex integration is a elaborate or a sophisticated use of this basic idea. So for the Euler equation, again, we want to replace inside this box the value c, so this value here, with an alternation of points in k, so values in what are represented as the vertices of this diagram. So if convex integration works for the Euler equation, it's because the differential constraints are not able to exclude oscillations such that as the one that I've shown in the simple example. What are those building blocks, the analogues of the oscillations in the simple example with a path? These are called plane waves. They're solutions to the linear problem, which I didn't write, but okay. So they're of a special form. They have a fixed direction, and so from the equation itself, you plug in this ansatz, and then you obtain the allowed direction of oscillations for your linear equation. This is called the wave cone, denoted lambda. And in particular, for the stationary Euler, if you plug in, you obtain some condition which looks like this. It's okay, nothing very complicated to calculate. Now, okay, so let's look at the simpler example where in your green box, so the value here sits on a segment connecting 2 points in k, and this is along a lambda direction. So what you do is you alternate between the values a prime and a double prime, and if you want to make your h minus 1 norm smaller, you just alternate faster and faster. But of course, all that matters is that the ratio between orange and purple is the same as the distance between this distance and that one. Okay. There's this caveat that the previous picture is correct in the whole plane, in the whole space, but you want to do this construction in a bounded box. I'm not going to go into details, but suffice it to say that you can localize this sort of construction up to an error which you can make as small as you wish. Instead of having a picture where sharp edges, you get something with a small error in this light gray color. But we don't need to worry about this. So let me now look at the general situation where the value that you want to replace inside this box is just the barycenter of points in k. But again, these branches have to be along lambda direction. So how do you use the previous construction? How do you adapt this? It's actually easy. You first alternate between a prime and b, but you don't want b. So what you do is you take a smaller box in the yellow region, and you replace b with an alternation of a double prime, a triple prime. Then you do this for another box, more boxes, and you can imagine that you fill up your yellow region with just blue and red values. So in the end, you've effectively replaced green with orange, red, and blue, and you've achieved what you want, up to an error which is as small as you wish. So some more terminology. K, as I introduced earlier, is the constraint set. Everything that you can generate as the barycenter of a diagram like this is called the lamination convex hull. So, okay, what I should say first is a diagram such as this one is called a prelaminate. There's a specific definition, but what's important is that the branches are all along lambda directions. That's the important restriction. And everything you can generate this way is the lamination convex hull. So obviously, everything sits inside the convex hull, and you have this inclusion in general. So I'm almost ready to state in the precise way of the H principle. So for the moment, let U be an arbitrary open set sitting inside the convex hull. X0 is the set of smooth subsolutions with values in this open set U. And you take the weak closure with respect to the L2 topology, and that's the set big X. And we say that the problem satisfies an H principle if the set of subsolutions which take values in K almost everywhere is dense. And recall that all of these things are actually, they correspond to solutions to the original nonlinear problem. So, okay, so that's what I mean by an H principle. And so from the previous discussion, it's clear that the larger the lamination convex hull, the more space you have to perform these oscillations and to implement your convex integration scheme. And indeed, this is literally so when the lamination convex hull fills up the entire convex hull, provided it's not trivial. It doesn't sort of degenerate to it does not degenerate. For in this case, the H principle, as I stated here, holds. And I'll give the sketch of proof of this fact. So as I said, a prelaminate is a diagram which looks like that here. And it's instructive to think of smooth approximations to prelaminates or to probability measures. So let's formalize things a bit. So if C here is the convex combination of points AJ in your sets K, and the weights are lambda J, then that induces a probability measure mu with weights lambda J concentrated in the AJs. Now the plane wave construction that I've shown you with the colors, the alternation of colors, so would produce a smooth function Wx, which approximate this measure in the sense that their respective actions on functions are approximately equal. So you can formalize things a bit. In particular, the mean of mu, which is just C, is approximately the average of W of x, which takes values in the gray region. But most of the time, it's here, here, and there in a precise ratio. And likewise, you can, the variance of mu is approximately given by the L2 norm of W, the whole thing squared. Now, a simple but useful observation for the proof of this folklore theorem is that if the point C is a distance epsilon from the set K, then the variance of the measure is going to be at least epsilon squared. So so you can quantify it's a lower bound of the variance from below depending only on the distance of C to the set K. So let's prove this theorem, or at least give an idea of the proof, the main idea. So, and this is by an argument using bad categories due to Bernkirchheim, mainly. So I'll call I of W the integral of Wx squared for any subsolution W. We'll use 3 facts. Fact 1, so the constraint set K here, the implicit assumption is that it's bounded, so you can use Banach-Alaoulu and conclude that it's symmetrizable. Fact 2, if I is a point of is continuous at W, and if Wj converges weakly to W, then the convergence is actually strong, and this is standard functional analysis. And third fact that are going to be used is that the points of continuity of this functional I is residual in the space X. And this is standard bad category theory. So I'm not going to prove these things. They're completely standard. So obviously what we want to show is that if I is continuous at W, at a subsolution in X, then all the values of X of W are going to be in K almost everywhere. And that's precisely saying that we have a solution to our linear problem. So if this set is dense, then all of these correspond to actual solutions to our problem. So we have a dense set of solutions. That's how you effectively show your H principle. So let then W be a point of continuity of the functional I. And for contradiction, let's assume that it stays away from K by an amount epsilon in some integral sense. Then because of the definition of X as the closure, we take an approximating sequence of smooth Wj's, weak approximations. And furthermore, by continuity here, we can arrange so that they all stay away from K by an amount epsilon, and again in some integral sense. So now I'm going to use the assumption that the lamination convex Hall is the whole convex Hall. So I'm going to do a bit of heuristics to avoid some technical complications, but this is saying that the typical value Wjx is a distance epsilon from K. So this is heuristics. Don't take things literally, but this is sort of the idea, that the typical point here is going to be at a certain distance K, let's call it again epsilon. Around this point, so that was somewhere here in the picture earlier, in the small box, because we have smooth things, then we can perform this plane wave construction. And this plane wave construction, if we take oscillations that are fast enough, we can have an approximating sequence in the weak topology, and also we can preserve with an L2 increment which is bound away from 0. And this depends only on how far the point is from K. Now we have a contradiction using the fact that I mentioned in the previous slide, because all these weak convergences are actually strong, and this is incompatible with this lower bound from 0 of the difference of these things. So you obtain a contradiction showing that this has to be 0. So that's in a nutshell the proof. I mean, there are some complications because this is an average sense, and you have to cut things into small boxes and prove things for those boxes and sum up and show that things are okay. But I think this gives a good idea what's going on. Okay, so the Lellis and Szekelyhidi. So I guess I should have mentioned earlier in the breakthrough of convex integration in the field of Euler equations is due to the Lellis and Szekelyhidi, and they showed an H principle for time-dependent the time-dependent Euler equation in 2007. It was published 2009, and there, if you read the proof, you realize that actually, so an outcome of the proof is that the lamination convex Hall agrees with the convex Hall. So the setting is a bit different, and it's a bit more complicated than that. So I'm not saying that they use the folklore theorem that of the previous slide, but it gives it's a good indication. It gives a good idea that convex integration should work. Okay, you have a lot of room to perform convex integration, to add oscillatory functions. So for the stationary Euler equation, the same holds for in dimension 3 and higher. And this is what we've proved, or actually verified, because the same proof actually works. We did with Laszlo. The difference is in 2 dimensions, where actually we can show that the lamination convex Hall is strictly smaller than the convex Hall. So in order to prove this, or give a sketch of the proof, I'll introduce a certain notion to make things a bit more precise. So if you look at the proof of the folklore theorem that I just gave, then you realize that what's sort of important is that the set U, so the open set U, where you want to perform the convex integration scheme, where you want to add those oscillations, should satisfy the perturbation property that is listed here. And let me point at the important bits in here in it. So U is such that any point in it, if you take any point in it, you should be able to perform this plane wave construction around this point. So this is what this says. W solves 2 means it's a plane wave construction. It should remain inside this open set U, which is automatic when you have the full convex Hall. And also that the increment, the L2 increment, should be bounded away, and you can quantify this in terms of the distance of that point to the constraint set K. So this is really what's actually used in the proof. And the question is, and when U is a convex Hall, then things are relatively, I mean, I've shown you that you can do this. So in dimension 2, to reformulate the previous claim, what we need to show is that the interior of the convex Hall fails the perturbation property. So I'll give a sketch with cartoon pictures. So the square here represents the convex Hall. K, the set K would consist of, say, the vertices of this square. And now you take a typical point on the boundary of the convex Hall, which is not in K. Now, if you calculate, you can verify by hand directly that there exists a segment, so that this point W tilde lies on a segment between 2 points in K, and that in fact it's unique. If you're not too careless, you can arrange so that this is not a lambda direction. So let now assume that the interior of the convex Hall satisfies the perturbation property. So what you would do is you take a sequence of points from the interior converting to your W tilde, and for each of these points, you can produce a prelaminate with a barycenter at this point WK, with a lower bound on the variance of this prelaminate. When you send K to infinity, because these branches are along lambda directions, heuristically speaking, you would conclude that this is a lambda direction, that this line would inherit the property that this is a lambda direction. But this, as I said earlier, this is not possible. So the actual proof is a bit more subtle, but this is basically the idea of the proof. So I've just proved that in 2 dimensions, the lamination convex Hall is not the full convex Hall. So what is it? Typically, there is a definition for these objects, but there's no, it's typically difficult to have a explicit characterization of those sets. And in fact, for this, in this case, we don't know what it is. It seems quite difficult to have a easily verifiable characterization of it. But in order to prove the H principle, the main result, what we do is we display an explicit open set we constructed by hand, and I'll show you in a minute what it looks like. It's an open set sitting inside the convex hull, which satisfies the perturbation property. And that's going to be the last part of this talk, to show you what this set U looks like. So, okay, so we're in 2 dimensions, remember. It's convenient to use complex notation. So V is a 2 vector, so we can represent it with a complex number Z. U is a 2 by 2 symmetric trace-free matrix. So again, we can represent it by a complex number zeta. And when you do this, use these identifications, you have new representation for the set K, which is just that Z has modulus 1. This is because V has modulus 1. And when you compute, you just verify that zeta has to be equal to Z squared over 2. Note that this sits inside R4. And likewise, for lambda, you plug in and just simplify, and you obtain that the condition that the point, or the vector rather, Z zeta is a good direction for oscillations, is that the imaginary part of Z squared times conjugate zeta be equal to 0. So these things sit inside R4, which is a bit difficult to visualize. And what we do is that we take advantage of certain symmetry. Namely, if you rotate Z by an angle theta and zeta by an angle 2 theta, then these sets are invariant. Okay? So what we're going to do is construct not U, but U inside a 3-dimensional slice. So we look at the 3-dimensional subspace in R4 for C cross C, where the imaginary part of the second component is 0. So for notation, Z has coordinates A and B. Zeta is a real number C. And it turns out when you plug in, you have a simple characterization of the lambda directions, meaning that A, B, C should be equal to 0. So now we're sitting inside this 3-dimensional vector space. We are going to look at the set K, and we were going to construct this open set U. How do we do this? So this is what it is. This is not a cartoon picture. This is actually what the set U looks like. So in red, I've represented the points in K. So here, here, and there. Now using the simple characterization of lambda directions within this 3-dimensional vector space, we can connect these 2 points because they have the same C coordinates as well as those 2 points. So this is in the set U because we can connect them along lambda directions. Now this point is in our set, and these points, they all have the same A coordinates, so you can include them in your set. And likewise for this point, the one here, here and there. So you have more connections. So for the moment, it's a collection of, I guess, 6 segments. And now we want to fill up. So we want to continue filling up this set with more and more lambda directions. And so to do this, we take a horizontal C slice. It's going to look like this. So for the moment, what do we have in this figure? We have the 4 vertices of the rhombus. They all sit inside a C-slice, so these points are connected along lambda, as well as, all the vertices are connected along lambda. And then once you've done that, you can fill everything inside this rhombus. And you do this at each horizontal slice, and you get this thing, somewhat discretized. But this is really what the set looks like. And you can verify that this is all you can get in this way. So the story is slightly more complicated, but essentially this is the set U that we use to perform, to implement the convex integration scheme, and we verify that it satisfies the perturbation property, and the machinery does everything for us from there on. The last slide is simply a list of reference. So the first one is the print on the archive. And the other ones are is a non-exhaustive list of references that you might be interested in looking into to get started in this area. And I'll thank you for your attention.
Questions?
I understand this thing is drawing these pictures, but usually the problem is that at one point you need to describe this that you construct there by a formula, so to be able to do something with it. So you have some kind of semi-closed description of this.
Yeah. So what I did not explain is so this is a picture of a three. So you first have the first step is you have these things which are 3-dimensional. So the picture is a bit of it's not quite correct. So you have this thing, and then because of the symmetry, what you want to do is you rotate this picture inside the inside R4, and then you have to include all the additional lambda connections within this new thing. But what makes this work is that within this 3-dimensional object, if you take a point inside this 3-dimensional object, you are going to have a prelaminate, and you can do a smooth approximation of these prelaminates inside this 3-dimensional thing, except, of course, you're going to spill a little over the 4-dimensional space. But because this is an open set, and then the way you define it, everything sits on an open set, you're fine. But it's essentially doing your plane wave construction inside this three-dimensional picture.
And you use the rotation symmetry to be sure that it's actually happening.
That it's an open set. If you don't have an open set, you cannot guarantee that you're. So you want to stay within an open set, and this is why you have this. It's slightly non-trivial to define, but okay, yeah. It's heuristically you rotate this picture using the symmetry inside R4. But again, you don't need prelaminates of very high order. It's just 3, I think, off the top of my head. It's essentially the picture is essentially 3-dimensional.
So in the time-dependent case, in dimension 2, then I suppose there is a case when you do not have this problem and everything is convex.
So in 2 dimensions? What is?
In 2 dimensions for the time-dependent problem, the one you mentioned.
Yeah.
So
There's no difference in with dimensions in the time-dependent case.
So you are in the same framework as in dimension 3 for the stationary problem.
Yeah, I would say that 3-dimensional stationary is the same as the time-dependent. Yes. Yeah. There's no difference. I wrote it as a corollary. It's really the same calculations.
So I have the question. Then, so apparently you have some constraints which are given, for instance, by modulus of Lellis square equals E of x, and this defines the set K.
Mm-hmm.
And well, the law just said these are the problem, so you can sense.
Mm-hmm.
And so my question is, would it be eventually possible to add some extra constraints and to keep still the geometry picture which will make the principle available and
yeah, certainly. Yeah, I haven't thought of specific additional constraint that would be natural. I mean, in an analogy to, I mean, your question applies, for instance, and this is what they've done, I think, Phil Isaac and Vlad Dikol, I believe. So it's a different convex integration scheme, but they try to, and there are different restrictions that they want to impose, but they, from an initial convex integration scheme, they want to construct, to adapt their construction with additional constraints which have to do with certain rotational symmetries. But yeah, for this stationary Euler equations, or I haven't thought about specifically specific examples of constraint that you might want to add. But presumably, 2 dimensions would be more difficult than